We've reached the most exciting part of the machine learning process, training. This is where we fit the model we have built and see if it actually works, so to speak. First, let's create a variable storing the number of epochs that we wish to train for. I'll call it num epochs and arbitrarily set it to 5. Next, we can fit the model. Similar to our TensorFlow intro, we will use the fit method. So, model.fit brackets. First, we specify the data. In this case, train data. Second, we set the number of epochs. So, epochs equals num epochs. Note that we have parameterized it in a neat way so we can clearly inspect and amend the number of epochs. Whenever we have hyperparameters such as the buffer size, batch size, input size, output size, and so on, we prefer to create dedicated variables that can be easily spotted when we fine-tune or debug our code. Okay, this alone would be enough to train the model. However, we also need to validate, right? It's a good thing we've already prepared the validation data. What we have to do now is include it as an argument to that same method, equal to the validation inputs and validation targets we created earlier. Finally, I'll set verbose to 2 to make sure we receive only the most important information for each epoch. Great! Let's briefly explain what we expect to happen behind the curtains. At the beginning of each epoch, the training loss will be set to 0. The algorithm will iterate over a preset number of batches, all extracted from the training set. Essentially, the whole training set will be utilized, but in batches. Therefore, the weights and biases will be updated as many times as there are batches. At the end of each epoch, we'll get a value for the loss function indicating how the training is going. Moreover, we'll also see a training accuracy, thanks to the last argument we added. Then, at the end of the epoch, the algorithm will forward propagate the whole validation dataset in a single batch through the optimized model and calculate the validation accuracy. When we reach the maximum number of epochs, the training will be over. Great! Let's run the code. What we see are several lines of output. First, we have information about the number of the epoch. Next, we've got the number of batches. It says 540 out of 540 because if we had a progress bar, that would fill out gradually. The third piece of information is the time it took for the epoch to conclude. On my machine, that's around 5 to 6 seconds per epoch. So far, so good. Next, we can see the training loss. It doesn't make sense to investigate it separately. It should be compared to the training loss across epochs. In this case, it is mostly decreasing. Note that it didn't change too much because even after the first epoch, we've already had 540 different weight and bias updates, one for each batch. What follows is the accuracy. The accuracy shows in what % of the cases our output were equal to the targets. Logically, it follows the trend of the loss. After all, they both represent how well the outputs match the targets. Okay. Finally, we've got the loss and the accuracy for the validation dataset. They are our check. We usually keep an eye on the validation loss to determine whether the model is overfitting. The validation accuracy, on the other hand, is the true accuracy of the model for the epoch. This is because the training accuracy is the average accuracy across batches, while the validation accuracy is that of the whole validation set. Great! To assess the overall accuracy of our model, we look at the validation accuracy for the last epoch. For us, it's a 97%. This is a remarkable result already. But can we do better? Let's try fiddling a bit with the model. We can change many of the hyperparameters, but I'll start from the hidden layer size. Instead of 50 nodes in each hidden layer, let's go for 100. Oh, wow! We've drastically increased the accuracy of our model. Amazing! Take a moment to appreciate this result. Imagine somebody came to you a month ago and told you, "Here are 70,000 photos of handwritten, squiggly, blotched, crooked digits. Write an algorithm that recognizes which digit has been written." What would you think about that? Probably you wouldn't know where to start. Now, with just a few lines of code, we've written an algorithm that gets 97 to 98 out of 100 digits right. This is a remarkable accuracy, considering the simple model we used. I'd like to conclude with a take of TensorFlow.org on the MNIST training. They show a model with an accuracy of 92% and ask, is that good? Their answer is, not really. In fact, it's pretty bad. Our model was one bit more complicated than theirs, and we achieved an accuracy of 97.5%. The question is, can you do better? Check the next lecture for instructions on how to do that for homework. Thanks for watching.